In this lesson on Java algorithms, we will learn about bubble sort. So bubble sort is a way to sort a group of elements, and the way it works is by comparing pairs of adjacent elements, and we swap their positions if they are in the wrong order. So this is how bubble sort works. We will look at an example to understand how it will work. So suppose we have these group of numbers 10, 8, 15, 7 and 9, and we need to sort them in ascending order. So we will sort in ascending order. So now ascending order means the final order should be 7, 8, 9, 10, 15. So increasing order. Now let's start with it. So this is where we have our first, this is our input, which is the group of numbers as you can see. And we will start comparing them pairwise. So which is the first pair we get? We start from here. So this is the first pair we get and we've just highlighted them in bold. And now are they in the right order? If they were in ascending order, should 10 come before 8 or should 8 come before 10? Obviously 8 will come before 10, so we swap them. And once we swap them, they look like this. So 10 and 8 have been swapped because they are not in the right order. Now once we have done it, we will move to the next set, which is now the array will look like 8, 10, 15, 7, 9, and we will now move to the next and check the next pair of adjacent numbers. 10 and 15, are they in the right order? Yes, they are in the right order, so we don't do anything. We move to the next. We now check between 15 and 7. Are they in the right order? No. If the array is to be sorted in ascending order, 7 should come first and 15 will come later. So we swap them. As you can see, we have swapped them. And then when we check the next pair, 15, 9, again they are in the wrong order. So we swap them. And we get this at the end of our first pass. So we will call each of them as pass. So at the first end of our first pass, this is how the array would look like. 8, 10, 7, 9, 15. So couple of properties we can see here. So the most important property we can see here is that 15 has come in its right position. So 15 is the largest number, and because it's the largest number here, it should come at the end, and that is what has happened. Rest, there is nothing we can say, but 15 has come in its rightful position. So now with this array, we will start again from the beginning. So in our second pass, so this is our second pass. So we have the same array 8, 10, 7, 9, 15, 8, 10, 7, 9, 15, and we'll again start comparing from the beginning. So this is our second pass which we are starting. So 8, 10, are they in the right order? Yes, they are in ascending order, so we do nothing. We move to the next pair. 10, 7, no, they are in the wrong order. So we swap them. So you can see we have swapped them. And now we move to the next pair, which is 10, 9. 10, 9, are they in the right order? No, they are not in the right order. So we swap them and we get 9, 10. And in this pass, we are not comparing with the last one because we know that in the previous pass we had achieved it. So now we are running it one less than the previous time. So now if you can notice, the last two elements are in their correct order, 10, 15. So they are the largest two elements and they are in the correct order. So at the end of pass 2, our last two elements are in correct order. At the end of pass 1, our last element was in the right order. At the end of pass 2, our last two elements are in the right order. Now let's start again. We will start from the beginning. 8 and 7, are they in the right order? No, so we will swap them. We have swapped them. 8, 7, 8. Then we have 8, 9. No, they are in the right order. Yes, they are in the right order, so we don't swap it and we will get it. So here the last three elements, as we would have expected, should have come in the right order. Coincidentally, in this case, all the elements in the right are in the right order, but at the end of pass 3, we will always have the last three elements. So we know that we will have them. Now for the first two elements, we have no idea whether they are in the right order or not. So we will run our last pass. So we will start with 7, 8. We will check for them. Are they in the right order? Yes, they are in the right order. So we will not swap them. Will we compare these two elements? No, we don't need to compare these two because we know in the last pass the last three were in the right order, so we don't need to do anything. So now at the end of it our job is over. So we have run through all our passes. So we run through 4 passes here because the array length was 5. So we run n minus 1 if the array length is n. So n minus 1 passes, and now you can notice that we have the array which is completely sorted. So now how do we look at the algorithm for this? So for I is equal to 0 and I less than len, what will we do? We will, within each for loop, we are running a pass. So this is defining our outer loop, and we will continue to run our passes like this. So whenever we go in, we will run our pass. And what do we do in this? We will check if aj is greater than aj plus 1. So that's what we did. If they were adjacent numbers we compared, and if aj was greater than aj plus 1, so this is when we are sorting in ascending order, so these are in the wrong order, so we just swap them and we continuously do them and we run it for the passes. So this is a bubble sort. Okay, now there is one more concept we want to understand about algorithms which we will initiate in this lesson, which is order of an algorithm. So order of an algorithm helps us in comparing two algorithms. And what is order? Order is defined as that if n is very large and n is the size of the problem, then how much time will that algorithm take? So like in the example we gave right now, so what would have n be? N is here the number of elements to be sorted. So suppose we say n is the number of elements to be sorted. Now how much running time it takes if we try and establish it in terms of n. So that is, this is the running time, and from the running time we will say what is the order. So the order is basically limit when n is very large, how will that function behave, and constants are ignored. So if we start with here, so if n is very large, this will become order of this will become approximately equal to 5n, and because we are ignoring this constant, so we will write it as order n. Similarly, if we have 10 n square plus 50 n, this is the running time, then if n is very large, this term will be much larger than this term, so it will be order 10n square, but we know we are ignoring the constant, so that is why we are saying order n square. Let's look at the third example, 8 log n plus 2n. Now if n is very large, we know this term will be very small relative to n, because we know if we take say 1000, if n is 1000, then log of n will be 10 and n is 1000. If n is say 65,000, we know 65536, the log of 65536 is 16, but n will be 65,536. So this is the term which will dominate, and hence it will be order n. Log 2 n plus 1000. Now for very large values of n, this will be much larger than 1000, and constants we typically ignore. So constants are typically ignored, so it will become order log 2n. And 2n cube plus 850n square. So how will we find it out? So obviously this term is much larger than this term when n is very large, so it becomes order n cube. 65 is a constant, it does not vary depending upon whatever is the value of n, so we call it order 1. So whenever it's a constant, that is referred to as order 1. And if you look at this term, so we have n log n, and we have log n. Now obviously this term will be the dominating term when n is very large, so this is order n log n. Okay, so if we just look at the order of certain, in the way we look at, so order 1, then it will be order log 2n, then it is order root n. Root n are very few algorithms which are root n, then order n, then n log n, then say order n square, and say order n cube. So this will give us an idea as how do the orders compare. As we discussed, algorithms are compared on the basis of order, and when two algorithms which are performing the same task have different orders, algorithm with the lower order is more efficient. So a log n algorithm is more efficient than a order n algorithm. or an n log n algorithm is more efficient than an order n square algorithm. Okay. So coming to bubble sort is the simplest sorting algorithm. It is inefficient as it is order n square. So bubble sort is an order n square algorithm, and the efficient sorting algorithms are order n log n. Okay. So the most efficient sorting algorithms are order n log n, and bubble sort is order n square. Okay. Why is it order n square? Because we compare the terms. So if you look at it in the first pass, so why is it order n square? If you want to answer it, in the first pass we will do n minus 1 comparisons. Then in the second pass we will do n minus 2 comparisons. In the third pass we will do n minus 3 comparisons, and so on till we do one comparison. So what is this? This is the sum of the first n minus 1 numbers. Now the sum of the first n numbers is n plus 1 by 2. So the sum of the first n minus 1 numbers will be n into n minus 1 by 2, which is equal to n square. So which will be equal to n square by 2 minus n by 2. Now we know this will be equal to order n square. So which is why bubble sort is an order n square algorithm, and efficient sorting algorithms are order n log n. Okay.